Hi, my name's Andy, and this is a video about the basics of asynchronous code in Python and how that lets you do amazing things like make 100 million HTTP requests all just with one thread running and without running out of memory or stuff like that. So that's just my example of what I did with it, but this video is really the basic stuff about how to use Python async, what the basic ideas are, concepts behind it. Or at least my understanding of them. So we're going to look at what is asynchronous programming at all. What does asynchronous programming look like in Python? Very briefly look at how you make HTTP requests within that asynchronous Python world. And then we're going to have a quick look at the motivating example, which is how I made 100 million HTTP requests. Yes, I really did. Without crashing my computer or even crashing the server that I was connecting to. Okay, so what is asynchronous programming? Well, it's the word that has come to mean asynchronous just means things that don't kind of wait for each other. But it's come to mean this relatively new way of writing code, or at least newly fashionable way of writing code, which does lots of things at the same time. But without using threads. So that sounds like a contradiction in a way. If you're used to writing, the only way that you make multiple things happen at once is that you start another thread and get that running, then you think I'm talking rubbish. What's really going on is something like this catchphrase that was taken from the Node.js world. So Node.js is one of the places which has made this kind of asynchronous programming fashionable. So this bloke on his blog, Felix, use this phrase, everything runs in parallel except your code. So what does that really mean? Well, it means when you need to kick off some kind of process like something that reads from disk or reads something from the internet or something like that, looks up something up in a database, normally you would kick that off and then sit and wait for it, and then you'd be told when it was finished. And you'd just be sitting waiting. You'd be holding onto a thread, just spinning there or sleeping, waiting for that thing to be ready. Instead of that, your thread gets completely suspended, some other threads get run while it's waiting, and then when the system is good and ready with your result back from opening a file or downloading something or connecting to the database or getting something from the database, then your code gets to run again, but not at the same time as any other code, just when its turn comes up. So it kind of works. So here's the main picture of how asynchronous programming looks in most programming environments. You launch some kind of I/O, as in input-output, something like loading a file from the disk. And that takes massively longer than just executing code. So while you're waiting for some stuff to come back from the disk, or even over the internet, which takes massively longer again, the computer's got plenty of time to run some other threads, see if they can get some work done. And then the normal way of doing this is once the thing your code is waiting for, like some information from the disk or the database or whatever, is ready, then you get a callback. So if one of your functions gets called by the system to say, here's the results of the thing you were waiting for. So that's how it works in Node.js in the most basic way. That's how it works in most asynchronous worlds. The thing that's a bit weird in Python is that callback is kind of hidden, so it doesn't look like you're getting a callback, but in a way you kind of really are. So we'll see how that looks. So here's an example of an asynchronous function. So it looks a bit like a function, but bear in mind it really is not like a function. It looks like one, but that word async before the def really means that this is nothing like a function in some way. In other ways, it feels like a function, so don't let me take that too far. But yeah, it's really not a function, and we'll see how, like, for example, calling it doesn't run it. We'll get to that. So for now, what I want you to get into your head is the thing I was just saying about you run some code, wait for something, and then you get a callback later. Well, in Python, what that looks like is you run some code, it runs all the way up to this word await, and that stuff will run, let's say now, at some point, and then later, the code after that await is going to run. This is where it would be a callback if it used callbacks. Really underneath it kind of is a callback, but in Python it doesn't look like it. It looks like just sometime later your code picked up from where it left off. Now, you should bear in mind for most of my examples, I'm using this function async.io.sleep, which basically means wait some amount of time and then later carry on. That in a way that's quite a bad example because it doesn't really do anything. Most asynchronous functions don't just sleep. They go off and load something from the disk or something like that and give you back a result. The reason I'm using sleep is because it's really simple to use in my examples. But I hope when you see sleep, you'll substitute that for something like load something from a file on the disk or over the internet. So my main point of this slide, do some stuff until you get to the word await, and then essentially your code will just stop there, and then later on it will carry on as if it had never stopped, and potentially with some information that came back from that asynchronous call. So sleep doesn't give us back any information, but reading from a file would. So there could be some return from that await that you get to use. Okay, so a little bit of terminology, some of the words that you'll read when you get to the documentation. There are various things which you might or might not see depending on how up-to-date documentation you is, because the words for these things have changed. By the way, I imagine that this video will go out of date and the words will gradually improve, because I've seen a lot of improvement. I've seen this stuff get less confusing as time's gone on, starting with Python 3.4 where it was unbelievably confusing. 3.5 it added the keywords await and async, which already made it less confusing. In 3.7 you've got some really cool stuff we'll see later on in this video that make this easier, and what you'll see is that things get talked about in recent stuff as tasks, in older stuff as coroutines, and kind of in between potentially as features. So you might still see those words coroutines and features. Those concepts still exist, but tasks are the kind of more high-level thing that you're more likely to see if you're just writing code that uses this stuff. Anyway, all those things, coroutines, features, and tasks, are just things that you can wait for. So by which we mean something that can go off and run, and then later on you can get a result back from it in that kind of asynchronous way that we saw in the previous slide. Other words you're going to need, there's this thing called the event loop, and the event loop is the thing that runs these coroutines, features, or tasks, or whatever stuff that you're going to wait for. So instead of you running them like you normally do with a function, you kind of give them to the event loop, and the event loop runs them, and that's how it manages to pause them, do some stuff in the middle, and then come back later. You can't just execute them on the Python interpreter, because the standard Python interpreter doesn't know how to like pause something and continue it later. That's a feature of an event loop, not of just the standard Python running code thing. So how do we write an async function? So this is exactly the same example we saw before. I'm just emphasizing a different part of it. So you write something which is called a coroutine function. It looks like a function. It has this def keyword that you're used to with writing functions, but before that it has the keyword async, and that means this is not a function at all. This is what's called a coroutine function, which essentially is a function that needs to be run by the event loop instead of just being executed normally. Inside any coroutine function you're almost definitely going to have this keyword await, because otherwise why are you writing a coroutine function? Why are you not just writing a function if you're not going to wait for some kind of async thing to happen? So in this example we're waiting for sleeping. So the way you wait for something like that, the way you say stop executing here and go off and do something else, do whatever you like and come back to me later, is by saying await. So the two keywords async and await are what kind of mark out this thing as a coroutine function, not just a function. If you run that thing, so we've defined that coroutine function mycoro on the previous slide. Here we're just calling it. When you call it, it doesn't run the code that's inside that coroutine function. This is why it could potentially be confusing. When you call it, what it does is it creates a coroutine object, which is essentially an object that can be given to the event loop. So you don't give the function definition to the event loop, you give the result of calling that function to the event loop. So basically what I'm saying is when you say mycoro brackets 3, it doesn't run it. What it does is makes an object that's ready to get run by the event loop, and we'll see how to do it. The way you actually kick it off is you pass it to the event loop, and the way you do that, it differs depending on your Python version. If you're lucky enough to have Python 3.7, you get a name which seems fairly sensible to me, which is create task. So you get hold of this variable c by calling the coroutine function, so that kind of just wraps itself up in something that's ready to be run. And then in your older versions of Python you call async.io.ensure future, which is weird because it doesn't return a feature anymore. I'm sure it used to at some point. I think, maybe I'm wrong. Anyway, ignore that. and then if you're in Python 3.7, you can call create task. But bear in mind, even that name create task, which I prefer, doesn't really give you the impression that I feel you need, which is it doesn't just create a task, it starts running it. So not only does it give you an object that you can wait for, which is this task object, so you can use the keyword await with that, but also it sets it off running. So it gives it to the event loop and says, run this, and when someone awaits the task thing, the thing that gets returned from create task or from ensure future, when someone awaits it, then what they'll get back is the return value of that coroutine function that we defined. Okay, so are you with me so far? We've got the ability to define something called a coroutine function by using async before the word def and then awaiting something inside it. That makes you a thing. Makes you a coroutine function definition. Then if you want to actually make a coroutine object, i.e. something that you can run in this async way, you call it, like on the first line here. And then to actually kick it off, you call ensure future or create task. That gives you back something that you can await. But if you run that program that I showed you just there, it'll give you a nasty error message. So the reason why is because the event loop system keeps track of stuff that you've kicked off and makes sure that you actually do await those things. So you've got to wait for something that you've started. You can't just let it trail off and disappear somewhere. And that's generally extremely useful because if you've forgotten to await something, that generally means you've done something wrong in your code. So here the warning that we're getting is basically saying you kicked off this thing called myCoro by calling create task, but then you never waited for it. So we've seen how you await stuff in the middle of some async code, but how about just in a kind of big, broad, I'm writing like a hello world style program, or at least what's the outer scope for all this stuff. What you have to do is you have to say run until complete. So basically, the top line here is doing all the stuff we've already seen in the old versions of Python Way. We'll see the new versions of Python Way in a bit, and it looks a bit nicer. So basically, we've defined myCoro somewhere else, not shown on this slide. We're calling it with an argument of 1, and then we're calling ensure future to kick it off. And then in order to wait for it, we have to get hold of the event loop by calling get event loop, and then we have to call the run until complete method on the event loop, which basically says just block until task is finished. So we're not getting any benefit from being asynchronous here because all we're doing is just waiting for task to finish. And then you have to call loop.close. So basically, to wait for something at the very outer scope, you say run until complete. But better, if you're lucky enough to be using Python 3.7 or above, you can wrap up all that stuff that I just showed you into one call, which is called run, which in the 3.7 documentation, it says it's unstable, so that may change, but it seems like a pretty good way of saying it to me. I want to run this thing and wait for it to finish. Just go ahead and do that. You don't have to type all those other lines of code. So that means that your Python 3.7 makes a bit more sense, maybe. It's a bit easier to read the code of what you're doing here. You're basically saying make this coroutine object out of this coroutine function definition that I made, give it the argument 1 for when it does run, and then run it and wait for it to finish. So that's the kind of top level world of how you run some of the stuff. That would be how you kick it off. But it's not very interesting if we're not doing interesting stuff inside it. So yeah, that's what happens when you run it. Instead of giving you that error message I showed you before, it prints out the messages that we got it to print inside it. Okay, so that was how to create a coroutine function, how to wait for other coroutine functions inside it, and how to run it and wait for it to finish. So other things you might want to do, you might want to combine together some of these coroutine functions into another thing that you can wait for. So there is this thing called asyncio.gather, and you can give it a whole load of coroutine objects. For example, here we're calling myCoro with 3 different arguments, but we could be calling completely other things as well. You give it a list of stuff, and what gather does is it makes a thing you can wait for, and if you wait for that thing, it will have actually waited for all the things you gave it and give you back the results of those things in the same order that you gave it to them. So here we can see the result of running that thing. So what gather does is it actually runs all 3 of the things we gave it in parallel, and you can see that number 3 happened to start first this time rather than number 1 starting first. And then 3, 1 and 2 all ran at the same time, finished at different times, potentially in different orders. and then you got back the results from gather in the order you gave it the task. So we gave the tasks in the order 1, 2, 3. The results back from those tasks, which is the string 1, 2, and 3, come back in the same order we gave it to. So gather gives you that guarantee that even though the things happen in parallel, you get them back in the order you gave them, which can be useful, can be not what you want. So here's how we run here's how basically we write functions that call functions, except these are coroutine functions that call coroutine functions. This is how you would structure a larger program where lots of things could be happening all at once. So what we've got here is a coroutine function called f1, which calls another coroutine function f2, and what f2 does is just the sleep thing that we're used to seeing. We do a bit of printing in the middle, but the important thing to notice here is that while f2 does an await for async.io.sleep, what f1 does is it does an await for f2. So this is how you can nest your functions, break your code up into asynchronous things that can all happen, or wait for each other. So f1 could have called all kinds of things and awaited each of them one after the other. That's like totally allowed. But here I'm just showing you how f1 can call f2. So what f1 can't do is actually just call f2 as if it was an ordinary function. Because remember, when you call f2, it doesn't give you back, it doesn't run the function, it gives you back a coroutine object which needs to be waited for. So here we're using a wait to wait for it. With me so far, leave comments. I know this is tricky. One of the reasons I'm making this video is that most stuff in Python is pretty straightforward. You don't need a video from me explaining how to do it. This stuff, it took me a while to get my head around it. I ended up writing a series of blog posts, and this video is a summary of some of those blog posts. And there's a link in the slides and in the show notes to the blog posts which go into a lot more detail. Okay, so here's me showing you what happens when we run the code that we saw on the previous slide. So basically f1 starts, and then as part of running f1, we wait for f2. So f2 gets started, then f2 finishes, and f1 now can stop waiting for f2 because f2 is finished, so f1 can finish. Okay, so that was words, lots of words from me trying to explain some different concepts, like what is a task? Task is the thing you wait for. What is the event loop? It's the thing that actually runs the things. What's a coroutine object? Blah, 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 blah. Coroutine function. You call a coroutine function in order to get a coroutine object. If pictures help more than words, maybe this will help. This picture should come with a caveat. This is kind of what my head uses to understand what's going on in asynchronous Python. It may very well not be what's really going on in asynchronous Python, but it helps me think about what's going on. So essentially, how I think about it is there's this stack of things that are in the event loop, either running or waiting to be run. So that's the stack of things in the middle. You can see the ones that say ready are ones where whatever they were waiting for is no longer blocking them. So something's happened, like the operating system has gone to the network and pulled down some stuff from the network and got enough bytes for you that you're ready to keep on running your code. And then the ones that say waiting in that middle column there are tasks where there's some I/O operation is still ongoing. They're not ready to run. So the way I think about it is that the event loop basically loops through all the things that it's got in that stack of things, or that list of things, and any of them that are ready, it runs the code until they're blocked, and then it goes on to the next one, sees if that one's ready, and then runs it until it's blocked, and so on. So a really interesting point here is that if you write code inside one of your asynchronous functions that doesn't do an await, and it goes on for a long time, no other tasks will be running while that code is running. So if you make a busy loop that sticks forever, for example, then your whole program will stop, because there really is only one thread running. The thread that's running is this event loop thread, which pulls bits of code from these tasks, runs them until they're blocked, and then it stops running them and goes off and runs something else. So that's how the event loop works. It goes through, in my head, it goes through this list of things, runs them until they're blocked, and then runs the next thing. So the thing that's actually parallel in all this is not the event loop. The event loop's doing things one at a time. What's parallel is that the operating system and things external to your Python code could be running all at the same time. So we see all these, the 4 tasks there that say they're waiting in the central column, they could all be waiting for different HTTP requests to be happening. Those would have all been launched one by one, but now they're all waiting to get their response back. So those things are happening in parallel, but they're not happening in parallel in your code. They're happening in parallel in the operating system. So that's what's so cool about this. Theoretically, at least, your code should be nice and simple because it doesn't have to deal with any of the horrible stuff about multiple threads modifying the same thing at different times. Because there's only one thread running. It's just that that thread could be running little snippets of different bits of code, which can get complicated. But maybe less complicated than with threads. So that's what we talked about, the central column and how that little event loop thing is looking through all the tasks. Then the other question is, how do things actually get onto that pile of tasks in the middle? And there's two main ways. One is that when you call create task or ensure future in the older versions of Python, that will create a new thing, stick it on the pile. And also, if you call await, two things will happen. Number one, the task that that is awaiting is going to kind of get put back on the pile, or it's going to change back to a thing that says waiting. And what it's waiting for is the new task that's been created. So here in my example, in my diagram, we've got this task 26 that's been created. That's going to go onto the stack, and that's probably ready to start. And then task 13 is waiting for task 26. So that is in a waiting state and it can't be run at the moment. But it's okay because 26 can be run. So maybe that diagram helps you. I hope so. Okay, so a little bit of background about how we make HTTP requests, and then we're going to get on to my example of why this is so cool, or one way in which this can be used, which demonstrates it's pretty cool. So here's a little bit of background that you need, which is enough code to be able to make an HTTP request inside this asynchronous framework. So you might know how to make an HTTP request in Python in a more normal way, or rather in the old-fashioned way, let's say. So this is you have to use a different library to make an HTTP request, and that's because you need to use code which does this await stuff inside it. You can't just take code. You can't take the old library that you liked using to make HTTP requests and expect it to behave asynchronously. That library, as part of the way it works, will block and wait for the HTTP request to finish and give you the results. So it doesn't do the await that we need to do. So instead you have to use a client session from the AIO HTTP library, and you have to use an async with block. So this is like a with block, a context manager, but when it starts up that context, it doesn't just create a client session, it awaits the creation of that client session. So basically some kind of asynchronous stuff could be happening. When it's finished and the client session's been created, then it'll carry on with your code. And then I've just done something slightly clever to fit it onto a slide. So I created a client session and called it S. And then also, as part of the async with block, like nested inside, I'm calling get on that client session with a URL to say, basically fetch that URL. When you've got the result back, put it into res. So you can see on the next line where we say ret equals await res.read, basically that res gives us something that again we waited, so that was the result of an HTTP request. And then we can call read on that, and we can have to await the result of read as well. So we've done three things. We created a client session, which obviously in your real code you would only do once, but here we're doing it every time we fetch a URL, just because it's example code. So we create a client session, then we use that session to begin an HTTP request to a URL, which is what get does, and then we call read, which is basically read the bytes from that URL that we've opened the connection to. And we're waiting for all three of those things, waiting to create a client session, waiting to open that connection with get, and then waiting to read stuff from that connection with read. And after we've awaited all those things, then ret is going to have the actual string that we pulled down over the internet from that URL. And then what we're doing is printing it out and returning. So that's this is a small program to make an HTTP request using async Python. And the reason we want to do that is because I want to show you how I made 100 million HTTP requests. So we don't just want to make one HTTP request, we want to make 100 million, or let's just say a lot, like too many to run them all in parallel, and too many to queue them all up in memory before we make them, because we're going to run out of memory. So let's have a look at what we've got, tools we've got as part of the Async IO framework that might get us somewhere along this path. So first of all, I don't want to queue up all the results, fetch all the results, and then deal with all the results, in a great big list because I'm going to run out of memory. But there is a function called asyncio.asCompleted, which instead of being like gather, where it gives you back a list of all the results, it can actually run some code whenever it gets back any result of the things that you're waiting for. So here's how we would write code to use as completed. Now in a minute we'll see this doesn't work, but here's how we would use it if it did work. So imagine we've still got that fetch function that I showed you before to basically download stuff from a URL. What we're going to do is we're going to call fetch lots of times in order to make coroutine objects that are going to download from that URL. Now, in the real example, obviously it'd be downloading from different URLs or doing something different in each request, not just making the same request 100 million times. But in our example here, we are making the same request 100 million times. So we've got this corows object, which is a list of calls to fetch. So we've done 100 million calls to fetch and kept them in a list. And then we're calling print when done and passing that list of coroutines into print when done. And what print when done does is it calls asyncio.asCompleted, passes in the list of coroutines that you want it to run. And what asCompleted does is it gives you back a result as soon as it gets any of them. So it's got 100 million things to do. As soon as the first one's done, it'll give you that back, and that'll go into that res variable in the for loop near the top. And then we'll await res, because you have to await things that come back from as completed, and then print out the answer. So in theory, this kind of looks like it would work, but you've probably already spotted the fatal flaw in this program, which is, well, there are basically two fatal flaws. The first one is I can't make a list of size 100 million with all my coroutines in it, because I will run out of memory. And secondly, the code that we've written there will actually launch 100 million HTTP requests all at the same time. And even if the server can handle 100 million simultaneous requests, which, by the way, it can't, my computer that I'm running from, the client, won't be able to handle that many outgoing requests. So this doesn't work. And that's why I couldn't do it until I did something, which is I wrote my own function, which is a bit like as completed, but has some extra features. And I called it limited as completed. And I will go over the outline of how limited as completed works in a minute. Not all the details. I wrote a few different versions of it actually, and I tried to get one incorporated into the Python standard library. And have a look at the blog post for how that went. Didn't happen. Maybe one day something like that will. There's more discussion continuing, but we'll see. Anyway, how you use limited as completed is there are two things. First of all, you can give it not a list, but something iterable. And secondly, you can pass in an argument to it, which says how many things to do simultaneously. So we can see where we call limited as completed at the top. We pass in this thing called tasks, just like we did before, except now instead of tasks being a list, it's a generator, which is basically an iterable set of things to do. The second argument, 1,000, is basically how many things should you do simultaneously, instead of just doing them all simultaneously like I did before. So you can see that near the bottom, what I was saying about how corows, which used to be a list, is now a generator. So it looks similar, but it's got round brackets. But basically what that means is when we try and iterate through corows, instead of corows already being a pre-filled list of 100 million results of running fetch, every time you ask for something from corows, it'll run fetch at that moment. So it sort of lazily runs it. So what limited as completed does is it iterates through tasks, but it only has 1,000 of them running simultaneously. And when you write code a little bit like this, with some kind of non-slide code elements to it that I added as well, to make it, for example, not making the client session on every fetch, I was able to make 100 million HTTP requests to my example server that I had built, which had an artificial delay inside. So the server delays you, just to demonstrate the kind of way it would work, between 1 and 3 seconds on every request. So these requests are sort of non-trivial in length. I ran it to make 100 million HTTP requests. It took about a weekend. When I came back, it was done. When I tried to run the previous example that I showed you before, it just crashed. because it ran out of memory. So this works kind of. You can make a lot of HTTP requests. I actually did something similar to a real service. The reason I was doing this was because there was a service at work that we needed to get a lot of results from. Maybe not 100 million, but too many to fit in memory. And I wanted to make the requests in parallel, but I didn't want to make loads of threads and stuff like that. It's horrible. So I thought I'd try this out. Found out it's hard to understand, but really cool and useful if you can understand it, and hence this video. So what I promised you is that I would talk to you a little bit about how limited as completed works. So what limited as completed is a function which takes in a generator of things that can be awaited and limits the number of concurrent tasks. But what it does is it awaits those awaitables from the generator and gives you back the results as soon as it gets any results. So here's a sketch of the implementation, and look, see the blog post for some examples of ways it got implemented, and actually see some linked blog posts from other people who did a better job of implementing this after I wrote a blog article. So it's a very cool, like, internet thing where people. My blog post was based on one by someone else, which you'll see the link to in my blog post. And then a couple of other people have written stuff based on my thing. It's really cool. It's like the internet works. So here's how limited as completed works. It takes in a load of coroutines and a limit, and it takes a slice. So futures is a slice of size limit. So in this case, 1,000 things. So it actually does kick off 1,000 things in parallel in order to make that list called futures. And then it basically calls this first to finish function until there are no more things to do. So until that slice has become small. So what first to finish does is what we do with first to finish is we yield it. So that means this function itself, limited as completed, is a generator rather than a normal function. So you can write a for loop saying for blah in limited as completed blah, which is actually what we did a couple of slides ago. So what first to finish does is basically waits until one of those 1,000 things is finished. When one of them is finished, remove it from the futures list and add a new one to the futures list, which is why the futures list never gets short until we've actually run out of stuff to do. And then once it's done that, it returns the thing that's finished. And the reason I'm not showing you the detail is because the way it waits until something finishes is a bit horrible and ugly, and actually some other people's examples are better. But anyway, that's kind of a general idea of how limited as completed works, or one way to implement it, which does work. As I said, you can get much more detail about all of this code, and I also go over the concepts. If you check out the link to the blog post, look at, search for Andy Balaam, search for artificialworlds.net. You should find my blog. Search for 100 million requests AIO HTTP, and you should find the blog post as well, maybe, or someone linking to it, hopefully. So if this stuff is unfamiliar, going over again, like what's a task, what's a future, what's an event loop, what's await, what's async, blah, 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 might be useful in written form. Have a look at that. And also read the links from people who've built on what I did and read the thing that I was building on when I wrote that blog post. A little bit more about me. You can support these videos by donating on Patreon if you want to. You can make me happy by playing my game Rabbit Escape, which is on the Google Play Store, also downloadable for PC. There's a free version you can download, or you can pay for it just because you want to. You don't get anything more if you pay for it. Like, subscribe, follow my videos on YouTube. Have a look also on PeerTube. All my videos are on PeerTube as well. Or not all of them. I'm moving them gradually, but my new ones are going on PeerTube as well, and my old ones are gradually going on there. Read my blog at artificialworlds.net/blog. Find out about projects, open source things I've done at artificialworlds.net. Follow me on Twitter, Andy Balaam. Follow me on mastodon.social, much more interesting place, which is a bit like Twitter. Andy Balaam at mastodon.social. Have a look at my GitHub. You'll find about the tiny little programming language that I wrote in order to learn about writing programming languages. Also look me up on gitlab.com. You can find all this stuff. If you follow me on something like Twitter or Mastodon, you'll see links to stuff. If you read my blog, most stuff goes on there. If you just want to see a whole massive brain dump of everything I've done, Have a look on artificialworlds.net. Listen to my podcast, The Good Robot Andes, where we talk about film and tech. Recent one was about why you should ditch Facebook because they're manipulating your behaviour. Search for The Good Robot Andes to find that. Have fun. See you next time.